All right, so for our gases, it's pretty short, but it's short for a reason. It's very cut and dry. So when I get done and you say, "Wow, is that it?" Really, that is it. It's just kind of a background because gases just have a couple extra laws that we need to consider. All right, so
Okay.
number one, we are going to talk about, hey, what is pressure? And then we'll do something called the kinetic theory of gases. And then Pivnert, the ideal gas law. And then we'll go into something called the empirical laws. So those all go together. And then I'll tell you, hey, guess what? Really, they're not ideal. They're real. Ha ha ha. I know, it sounds so funny. And then we'll talk about partial pressures and then molecular speeds. So there is only one handout for this particular chapter. All right, pressure. What in the world is pressure? Now, I know everybody has an idea of what pressure is, but generically, it's the force exerted per unit surface area. So force is equal to mass times acceleration. Okay, so if we were in physics, that's what we would call it. We measure it, of course, in the SI unit of a Pascal, which is a kilogram per meter second squared. Commonly in lab, we use millimeters of mercury. Another one that's very common is the torr. And then, of course, there's even another one that's the atmosphere. And I think it's, one of the biggest units that has 6 billion different variations. And there's just a different one for every instance. At least distance, we would say miles and kilometers. Well, per pressure, who knows? Hey, it's pounds per square inch, it's atmospheres, it's torrs. There's just so many variations of it. So, number one, if you look on your reference sheet, you'll be able to go back and forth between all of them. These are the ones most commonly used in chemistry. So our pascals, our millimeters of mercury, our torr, and our atmosphere. And I give you some of the others, but those are the basic ones. So let's just try one. So if I have atmospheric pressure usually is listed in millimeters of mercury. So if atmospheric pressure was 773 millimeters of mercury, how many atmospheres is that? Well, we know that there's 760 millimeters of mercury in 1 atm. And so where's my calculator? All right, hold on, that just jumped me off the screen. Huh. Well, let's try this again. All right, Elizabeth, can you see the pressure screen again?
All I can see is your files.
Okay. Why? Okay, let me try it again. How about now? Did it go back to the pressure page?
Yeah.
Whew, I don't know what that was, but suddenly my screen went black and it went to the page of death. All right, so the problem we had was 770, I think, divided by 760. Oh no, it was 773. So 773 millimeters, 760. And to sig figs 1.02. Right, so
Yeah,
there's
that's what I thought.
okay, there's nothing special about that. It's just going back and forth between units.
Okay.
All right. Now, pressure is very interesting because it's per square unit area. So I'm going to draw you my very pretty picture of a stiletto heel. Whoa. Okay, that does not look like a stiletto heel, but would you rather me stand on your hand with a stiletto heel or a sneaker?
Definitely a sneaker.
Definitely a sneaker. So even though it's the same mass pushing down, pressure, we have to remember, is specifically defined per unit area. So it's not the total area, it's per unit area. So yes, it's the same amount of mass pushing down, but the force is in one specific area. So kind of keep that in mind as we're talking about some of these other things. So how are we going to measure it? So we can use either a barometer, which is open to the atmospheric pressure, or we can use a manometer, which basically gives us the reading of a sealed container. So if you hear it on the news, oh, the atmospheric pressure is 770 whatever and dropping, that is just of the atmosphere. But if you read a gauge on a gas cylinder, that is technically a manometer because it is of a fixed cylinder of gas. And so, but the manometer has its purpose, but don't forget the manometer also, or the barometer will give it of atmospheric pressure. So we're going to use both of those. Both of those, they have very specific purposes. All right, just a little blurb about the manometer. A manometer, manometer is basically, I'm going to draw an ugly picture for you. They used to be made of mercury because mercury is liquid, but it's very hard to move because it's very dense. So what it would do is you would attach your cylinder or whatever. Here's what you're taking the pressure of. And then atmosphere is pushing this way. And so it has to equilibrate by how much the container is pushing, and it'll offset by atmospheric pressure. And then we could read the difference, and that would be the pressure of the container. And the idea still holds true. We just don't use liquid mercury very much anymore. And the one that you're probably most common with is called a sphygmomanometer. That's the blood pressure cuff that they use in the doctor's office. Crazy, huh? Sphygmomanometer.
Yeah.
Mm-hmm. That was one of my spelling words as a fifth grader. Oh yeah, so
Mhm.
missed it. So missed it. I know what fifth grader should be able to spell that. But all right, so you're very familiar with manometers. All right, if you wanted to build your own, what would you use? Now the key is it does have to be able to move, so you have to put a liquid in it. So the two most common, of course, in the past was mercury because it was a liquid, and water because not only is it a liquid, it is fairly dense and it's not toxic. Okay, so those are the two that we use most often. And if you wanted to figure it out yourself, you would put the pressure is equal to, now the acceleration of gravity, like how much is pushing down on it, the density of the liquid, and then the height of the column. And so you could actually calculate how tall would a water column have to be compared to a mercury column. Again, probably not very useful, but if you needed to, you could determine what liquid you could use. And then thermometers sometimes use alcohol. All right. What in the world is a gas? Why do we care? And are there any exceptions? So the kinetic theory of gases, the postulates of this are number one, gases are composed of atoms and or molecules whose size is negligible compared with the average distance between them. So basically, we are saying they are so tiny that you really don't have to consider their mass. Is that an accurate statement? No, but they are so tiny that it is a fair assumption. Okay, so gas particles pretty much have no volume. So there's number one. Number two, they move randomly in straight lines in all directions at various speeds. So are they all doing the exact same thing at the same time? No, they all have to move in straight lines. Okay, I don't care what direction it's going, but they can go in all directions and they can be at different speeds, but there's no corkscrews. Okay, so a little gas molecule isn't going to suddenly get a wild hair and, corkscrew off the side or anything. So we can at least know part of their trajectory. The forces of attraction or repulsion between the molecules, okay, those are called the intermolecular forces. Basically, they don't like each other. Okay, we are going to assume that if you have a diatomic oxygen sitting next to a diatomic oxygen, They don't care. They don't like each other. Who cares? They're just going to not interact. And again, that is an assumption, but it's a very good assumption. Number 4, the molecular collisions are elastic, which means if one gas particle hits another particle, they are going to bounce back off. They're not going to do okay, it's the bubble visual. So if you have two bubbles and they collide in the air, they almost attach to each other and they go wobble, 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 wobble. Okay. Gas particles are not going to do that. They're going to bounce just like two separate balls. They're going to hit off each other and they're going to go in their directions, and neither of them are going to lose any kinetic energy. All right. Do you know what I mean by the bubble, bubble, bubble visual, Elizabeth?
Yeah, yeah.
Oh,
Yeah, I gotcha.
yeah. Should I try and draw that? But it's just a great visual. It's a great visual. All right. If you want to measure how fast the gas particles are moving, good luck. You can't do the total, but you can certainly take the average, because kinetic energy is the energy of motion. And so the average kinetic energy will tell you the average at any given moment. So is it a true, picture? No, but it is an average. So we call the average kinetic energy temperature. So when we measure temperature, that's actually what we're measuring. And lastly, these particles, they'll collide with the walls, and hitting something with surface area, hitting a wall, will actually help us figure out what the pressure is. Okay, so these collisions constitute what we call pressure. If it bounces off the detector, we can read that. If it bounces off the wall, it will just have the same pressure until it hits somewhere that is a detector. So do you have to recreate those word for word? Absolutely not. But the overall idea behind them is they're so small that we're going to assume they have no volume. They move randomly in straight lines. They are negligible interactions, so they don't necessarily like each other or hate each other. They'll come close, but they just ignore each other. The collisions don't bubble, bubble, bubble. They actually bounce off. And temperature is what we call an average kinetic energy. And then those gas particles, when they bounce off the wall, that bounce, what we can measure, is called pressure. All right, questions or thoughts on that?
No, I'm good.
Okay. And those are, that didn't say much, but that is a huge concept. All right. So now that we kind of have the idea behind them, we have an equation called the ideal gas equation, and it's in your reference sheet. But the ideal gas equation, keep in mind, says ideal. And so we are going to do two assumptions. It is going to assume that there's no interactions and that there is very small pressure. Okay, so I can't use extreme pressures, and I can't use particles that really, really are attracted to each other. But for most gases, under normal conditions, the ideal gas equation works really well. But keep in mind, it does use assumptions. All right, I call it PV. PV equals nRT. And so P is pressure, V is the volume, N is the number of moles, and R is something called a gas constant. Now, remember, I said there's all sorts of pressure units. Well, here is the same constant with two different units. If you're ever dealing with gases and pressure, you'd use the top one, 0.082058 liter atmospheres per Kelvin mole. If you're ever using pressures in energy calculations, you use 8.314. And again, that's under the pressure under the green sheets. And again, that's a constant, so you can just look that one up. And then, of course, T is in temperature in Kelvin. We may have to make sure that our gas problems are always in Kelvin. If I give you a Celsius, it always needs to be converted. And so I'm going to go to the whiteboard. We're just going to do a practice problem. Now, depending on your personality, you are either going to want to solve for the variables ahead of time, or you like to plug all the numbers in and then solve. So I'm going to do it both ways. So I have a gas, and it is, it's going to be oxygen gas. and I have 16.8 grams of it in a 2-liter container at, you know what, we'll say 25.5 degrees C. All right, what is its pressure? All right, first we have to identify the concept. Oh, look, I'm talking about gases. All right, am I talking about ideal gases or, well, we haven't covered anything else yet, so right now that's your only answer. Is there an equation that goes with that? Yes. PV is equal to nRT. The moment we write the ideal gas equation, two things have to pop into our head. Number one, there's assumptions. Number one, we're going to assume that they're so small, okay, that really it's negligible, and that I'm not using extreme pressures. Okay, so that looks like this problem. What am I trying to find? I have grams, I have liters, so I definitely know this one, and I have temperature. R is just a constant. And remember, if you are ever given a mole, or sorry, if you're ever given a gram, you can convert to moles. So you're also given that one. Oh, so what must I be looking for? I must be looking for the P. So you might be the type of person that right now says, oh, okay, P is equal to nRT over V, and then plug them in. Or you can plug it in and then isolate variable. It does not matter, but R is 0.08, let me see, 0.08, wow, 0.0821. Double check me. Is that the gas constant rounded?
I think so. Yeah.
0.0821. I don't know why that sounded so funny to me. All right, now keep in mind, I did round it because I didn't need very many significant figures. So I better make sure I am in liters, atmospheres, Kelvin, and moles. All right, so first of all, I'm in grams, so can't use that one. So step number one is just to get out of grams into moles, and I know there's 32 grams of O2 in every 1 mole of O2. So 0.525. All right, temperature is in Celsius, so 25.5 plus 273.15 is 298, basically 0.7 Kelvin. All right, my temperature is now good. My volume was already in liters, so that was good. So now I'm going to plug and chug. So my pressure is going to be 0.525 moles times 0.0821 liter atmospheres per Kelvin mole. And my temperature is 298.7 Kelvin. And I'm going to divide that by 2 liters. All right, my mole is gone. My Kelvin is gone. And remember, invert and multiply. My liter is gone. And I'm left with atmospheres. Is that the unit that I was looking for? Yes, because I was looking for pressure. So I'm going to plug and chug. So pressure is equal to 525. All right, how many sig figs? I only get 2, so 6.4 ATMs.
Okay, that's what I got to. I was like, I hope I get it because there's a lot of.
Okay, there was a lot of math in there. Beautiful. Brittany, how about you?
I haven't plugged it in yet. I'm still writing down. I'm trying to catch up.
Oh, sorry. Nope, that's okay. All right. So if I do a calculation, it comes out different, holler at me though. All right. So basically, under those conditions, what should the what should the pressure measure on that container? And it should be 6.4 atmospheres. Well, what if I didn't want it in atmospheres? Well, once you find it, convert it to whatever you want. Do you want to convert it to pascals? Do you want to convert it to torr? Okay, but this problem will always give you an answer in atmospheres. So the ideal gas equation. Sorry, had to take a drink. All right, let's try another one. Am I okay to delete it?
Yes.
Sorry, Brittany, was that a yes?
Yes, thank you.
Okay, you're welcome. All right, we are going to use our new tool. Okay, so PivNert, the ideal gas equation, is our new tool. It is going to relate pressure, volume, moles, and temperature. And I can play with any of those. Well, I can also play with variations on a thing. So remember, density is mass per volume. Molarity is moles per volume. Let me see. Molecular weight is grams per mole. And I can get all of those things out of PivNert because PV also equals G over molecular weight RT. Because remember, N is the mass divided by the molecular weight. So I'm just replacing the variable N with G over molecular weight. So if I want to solve for density, density is G over V. So I have to keep this one on the right. I'm going to divide both sides by V. And then I'm going to multiply the molecular weight and the R and the T over. So my V is gone, my molecular weight and R and T. So this equation can be derived to be molecular weight RT over, let me see, molecular weight RT. That looks funny to me. All right, my molecular weight goes up, my volume goes down, my RMT goes up. Yep, that looks right. All right, so I can also solve for density, or I could solve for molarity, which is N over V, which would be P divided by RT. And I could also find my molecular weight. So the molecular weight, you know what? I'm going to put that over here. PV equals G over molecular weight RT. So if I wanted molecular weight, I'd multiply both sides. And then I would divide this side by pressure and volume. Whoops, that's a P. And so it would be GRT over PV. Now the derived ones are not in your reference sheet, but basically I'm just using PivNert and I'm going back and forth between them. All right, do my derived calculations make sense?
Yes.
Okay. All right. So if I gave you grams, that's basically PivNert again. It's just I'm changing moles and I'm putting in mass per molecular weight. So we could do all those same calculations with derived units, which there's where I plugged in mass per molecular weight, okay? And then I'm deriving it for density. See, I knew my other one looked wrong. This is the correct one. Okay, so there's density. And then we could also find it for molarity. And I just want to jump to, you know what, let's do a problem before I jump. Make up a problem. What is the density of a gas if the temperature is 23.6 degrees C, the pressure is 748.34. And what else do I need? Yep. What is the density of a gas if it's at 23.6 degrees C and 248.3 torr? So again, I'm talking about gases, and I can assume that I'm using the ideal gas equation. So PV equals nRT, but I'm looking for the density. So I'm going to change that to PV equals G over molecular weight RT. And then I'm going to take the molecular weight up. And then I'm going to divide through by the RT and divide through by the V. And so G over V, which is density, is equal to E over RT. Oh, okay. Well, I know all those pieces. Do you know the pressure? Yes. Do you know the temperature? Yes. Okay, let's plug them in. Make sure my molecular weight. Sorry, I forgot the molecular weight right there. Aha. So I do need to know one more thing. So I'd have to tell you the identity because we need the molecular weight. All right, so if we want the density, it would be the pressure, but remember the pressure has to be in atmospheres. And right now it's in torr, so I know that there's 760 torr in every 1 atmosphere. So 748.3, 0.985. So 0.985 atmospheres times the molecular weight, and each oxygen weighs 16. So it's 32 grams per mole, all over R, which is 0.0821 liter atmospheres per Kelvin mole. And my temperature, which has to be in Kelvin, and right now it's in Celsius. So, oh man, I just threw my calculator. My calculator that is like so old. All right, so 23.6 plus 273.15, and so 296.8. Kelvins are gone, mole is gone, atmosphere is gone, and I'm left with grams over volume. Is that the unit I wanted? Yes, because that is the unit of density. And so 0.985, 32, 0.0821, 296. All right, so sig figs, I get 3. So 1.29. So density is 1.29 grams per volume. And in this case, remember, that's liter. Okay, because the unit comes out in liter. So it's grams per liter. All right, questions? Thoughts on how to use the manipulated Fibner?
I am good.
Okay, it's pretty straightforward. Brittany?
I think I understand.
Yeah, till we go and do problems, huh? All right, let's
Probably.
go on. We'll go on to the next one and then we'll come back and do some problems. Excuse me. All right, go back to the notes here. That is literally Pivnert. That's it. We just manipulate the equation to find our numbers. All right, now there's something called the empirical gas laws, and those are only 2 variables. So some scientists said, I would love to know what Boyle wanted to only know what pressure and volume would do. Charles wanted to relate volume and temperature. Gay-Lussac law is using pressure and temperature. And then there's one called the combined, where it's PV equals T. And so these are called the empirical gas laws, and they're just given the scientists' names. So you do have to, remember their names. So the reference sheet does not give their names. It just gives you the formulas. But Boyle's law relates volume and pressure. And so here's the idea behind Boyle's law. Pressure volume equals nRT for the first set of conditions. And remember, R is just a constant. Well, if you change those conditions, P2, V2 equals N2, R, T2, you can actually set them equal to each other because the R is the same. But that's too many variables, okay? We don't want to use linear algebra. So we are limited to 2 variables. So I'm going to keep N and T the same. So N1 is equal to N2 and T1 is equal to T2. So we're going to keep those two the same. And now we can say P1 V1 is equal to P2 V2 because the others cancel out because they're all identical numbers. So I can now put in numbers. So if I have, I don't know, 1 atmosphere in 2 liters, what will my new pressure be if I double the volume? If everything else stays constant, I can use Boyle's law. So P1 was 1 atmosphere. V1 was 2 liters. P2 is what I'm looking for, and V2 was 4 liters. So I'm going to divide both sides by 4. My liters are gone, and my second pressure is going to be 1 divided by 4, or 0.25 atms. So the power of the empirical is it takes it down to just 2 variables, and you can see how they're related by changing one of the conditions. Now, just as a little reminder for math, if they are on opposite sides, okay, so PV equals nRT. If they're on opposite sides, those are called directly related. Directly related. Because if you increase one, okay, so if you increase the left side, mathematically, you also have to increase the right side. So if they're on the same side, there's going to be difference. So if they're on opposite sides, they're directly related. If they're on the same side, they're inversely related, which means we're looking at the pressure and the volume now. I'll change colors. So if the pressure goes up, mathematically, the volume has to go down to keep the same constant. All right, so if we hold everything else the same, if I increase the pressure, the volume has to go down. If I decrease the pressure, the volume has to go up. So let's look at this one. I started at 1 atmosphere with 2 liters, and I increased the volume. I increased the volume, and if that's true, the pressure had to go down, and it did. It went from 1 atmosphere all the way down to 0.25 atmospheres because they're inversely related because those variables are on the same side of the equation. And so that is Boyle's law if you want to play with pressure and volume. Charles' law, he wanted to play with volume and temperature. So that means everything else had to be held constant. I'm going to jump over the whiteboard. All right, so PV equals nRT. All right, volume and temperature are directly related. And if you want to only play with those two, you have to solve it for them to be on the same side. So I could go V over T is equal to NR over P. Or, okay, there's nothing wrong with doing this. We could do T over V is equal to, let me see, T over V, which is equal to P over NR. Okay, it does not matter which way I go. This is held constant. So if I want to change conditions, I can say V1 T1 is equal to V2 T2, or T1 V1 is equal to T2 V2. Okay, there's no difference. Why would I use one over the other? Well, some people don't like to solve for variables in the denominator, so just use the other variation. So for instance, if I had a system at 25 degrees C at 2 liters, what would happen if I increase the temperature to 30 degrees? What would my new volume be? All right, so it is talking about the gas laws. I'm holding some of them constant. The only two I'm playing with is temperature and volume. So I must be playing with Charles' law. Do I know an equation for Charles' law? Yes, it's one of these two variations. All right, which pieces do I know? The original volume was 2. The original temperature was 25. The new volume is what I'm looking for, and I know this one. So in this case, I think the equation on the left is a little easier because the V2 is in the numerator. But stop. If you are ever dealing with gases, you must be in Kelvin. Now, I'm going to solve this problem both ways just to show you that, yes, it does matter. And so let's say I forget. Oh, I'm just going to use Celsius. So I have 2 liters over 25 degrees is equal to V2 over 30 degrees. And so V2 turns out to be 2.4. All right, I would expect that. If I increase the temperature, okay, if I increase the temperature, oh, the volume should have done what? V and T are on opposite sides. So if you increase one, you have to increase the other. Oh, yeah. So 2 to 2.4. That makes sense. All right, so that's if I do not put it in Kelvin. This is the correct way because the gases should always be in Kelvin. So it's 298.2 and V2 over, I believe it's, yeah, 303. Again, I'm going to multiply 303.2 on both sides. So 2 times 303.2 divided by 298.2. And my answer is something wrong. All right, 2 point, how many sequence? V2 is 2.0 liter. What? See, I told you something was wrong. 2 liters times 303.2 divided by 298.2, and I still get 2.03. Wait, hold on just a second. Sorry, somebody was knocking on the door. All right. Well, I think that looks very different. So in this case, 2.03. I'm going to put the sig fig, even though I don't get it. This one increased by 0.4, and this one only increased by 0.03. Now, technically, it did increase. Okay, so technically it did increase, but definitely not by as much as over here. This is the correct answer, by the way. That's the correct answer. But let me show you why. Erase this top portion. Well, maybe. All right. This is what the math should look like. 2.0 liters over 25.0 degrees C plus 273.2 degrees C Kelvin all over V2 over 30 degrees plus 273.2. All right, and so the V2 equals, I like to do 2.0 times 30 plus 273.2 all over 25 plus 273.2. All right, the question is, do those just cancel out? And as far as order of operations are concerned, the answer is no. So the reason you cannot be in Celsius is because that is an addition or a subtraction step, not a multiplication and division. And so you have to take into account orders of operations. And so just always be in Kelvin so you don't have to worry if that's going to be a problem. Always be in Kelvin if you're dealing with gases. Okay, always be in Kelvin. Wait a second, Joey. What? It's an order of operation thing. If you just do 30 and 25, that's basically saying you said those were the same number and just cancel them off, and they're not. You have to do addition and addition and then divide because I'm violated the order of operations. All right, so there's Charles' law. Any questions on why we have to use Kelvin or Charles' law?
No.
No.
Perfect. Okay. Let's do the Gay-Lussac law. So we have played with pressure and volume. We've played with volume and temperature. Let's play with pressure and temperature, which means these three have to be kept constant. And again, pressure and temperature are on opposite sides, so they're directly related. So I could solve it to be P1 T1 is equal to P2 T2, or I could go the other direction and I could say T1 P1 is equal to T2 P2. All right, and then we're down to the same thing. Well, what numbers do we want to plug in? Temperature always has to be in Kelvin. I don't care what equation you're using. But I can plug any unit in for pressure or volume. Because those, they don't have an addition term, and so those just cancel out. But Kelvin, remember, that's an order of operations thing, so I have to always be in Kelvin. So I'm going to give an example of, let's do torrs. So my first torr is 738 torr at 25 degrees. What is my new torr? No. If I change the pressure to 750 torr, what is my new temperature? All right, so I'm looking for T2. Over here, this equation has it in the denominator, and this equation has it in the numerator. Again, it does not matter, but you can use the one on the numerator if you so desire. So T2 over pressure 1. Do I have to convert to atmospheres right now? No, and I will show you why. So my T2 over P2, which is 750, is equal to 25, well, whoops, 25.0 plus 273 over 738. To get rid of this torr, I'm going to multiply both sides by torr. And notice the torr goes away. And this torr goes away. So why do I spend the time to convert it out? You don't have to. Okay, not for the empirical laws, except temperature, because there is still an addition as part of that equation for temperature. All right, so T2 is equal to 298.2 Kelvin times 750 torr divided by 738 torr. And before I do the calculation, I'm going to ask myself, if I increase the pressure, okay, so if I increase the pressure, what am I expecting the temperature to do? They are directly related, so I'm expecting it to increase. So I do my math. And I get 303. So yes, it increased from 298.2 to 303. And that is the Gay-Lussac law. That's pressure and temperature. The last one doesn't get a fun name, but we're going to play with P, V, and T. So I'm going to isolate PV over T is equal to NR. So these are going to be my constant. So P1 V1 over T1 is equal to P2 V2 over T2. And that's called the combined. Because I'm doing all of them together. That's called the combined gas law. All right, jump to the notes, make sure I get there. All right, so we saw Boyle's, we saw Charles, we saw the Gay-Lussac, and we saw the combined. The last one, we'll talk about this next time, is can't I play with moles? Oh, look, that would be called Avogadro's law. And it has a fun little unique twerk about it. All right, are there any questions about the ideal gas equation?
I don't think so.
Okay, how about the empirical?
I think I'm pretty good, but probably when I do the handout, I probably will have some. But like right now, it looks good.
Okay, Brittany?
What did I miss?
Okay, so I started with Pivnert, PV equals nRT, the ideal gas equation. And that's where I had the whole equation and I just solved back and forth for the different ones. And I think you hit everything but the original pressure equation that I tried.
Then I think I get it.
And I promise it really is supposed to be that easy. Okay. All right. So I will post this recording actually on Canvas. And then tomorrow I will pick up where we left off, unless there's a whole bunch of new people. And then I will do this variation in just different examples and then just do it again. So Brittany, if a whole bunch of people get on, we will just start from the beginning again.
I'm in class at noon tomorrow.
Oh yeah, that's right. Okay. So it'll just be a repeat and then I will see you again on Wednesday. Okay.
Okay, thank
Okay.
you.
You are
Thank
so
you, Jelly.
welcome. Okay. I'll either see you tomorrow or I'll see you on your Wednesday. Okay. Bye.